Hello and welcome to next lecture on pattern recognition. Last class we have been discussing issues about assessing classifiers or regression function models, in general any model that we learn from data, and we looked at some very generic issues of which are independent of any learning algorithm. For example, no free lunch theorem and so on, which tell you that there is no such thing as the best classifier learning algorithm. Essentially, each algorithm, if it does well on certain kinds of pattern classification problems, it has to do badly on certain other classification problems. So, every algorithm has its own niche applications, and that's nice. We also looked at this so called bias variance trade off in getting a good model estimated from data, and after that we were looking at, in practice, how does one assess length models, right? Apart from all those theoretical issues, somebody gives you some data, and we have to learn a model from it, a classifier, regression function, whatever, and then we have to ultimately decide whether what we learned is good enough, what kind of estimate is directly likely to give. As you also seen, learning a model involves two steps: a model selection and a model estimation, right? So, essentially we need to use the training data for model estimation, model selection and model assessment, right? What does that mean? We have to first choose a class of models, right? A class of models would mean all the parameters of the model should be fixed. So, neural networks is not a class of models, but neural networks with a single hidden layer with 5 hidden nodes is a class of models, right? So, we have to first choose the model parameters. Similarly, a Gaussian kernel with sigma is equal to 10 is a specific model class. And to select a suitable model class, and then within that model class, we have to learn a specific model. That is what we have all the algorithms we have been considering so far are given some training data. How do we learn a particular model from the class of models that we have decided to learn from? And then we also have to assess how good the final learned model will perform, right? So, the idea of model assessment is that we need to use the training data not only for model estimation, meaning all the learning algorithm that we have been discussing throughout the course, but also for selecting suitable model class and also for estimating the true risk or the final error that the learned model is likely to have, right? And the reason why this is an interesting or difficult problem is that the training error is not a good indicator of the suitability of the learned model. Obviously, because all our algorithms are designed to minimize the training error. So, whatever idiosyncrasies or noise is there in our training data, our algorithms try to tune for that, and hence we may get a very low training error, but that does not necessarily mean we will do well on unseen patterns, right? So, essentially when the model complexity is large, it is possible that we can get very low training error, but the test error, that is error on new unseen data, would be large, right? So, this is the basic issue, okay. We actually seen last class, but this graph is worth seeing many times. This is a very important graph for model assessment. Essentially, the training and test errors behave like this. For a given number of examples, as I am increasing the model complexity is along x axis and error is on the y axis. So, the red is the training error. So, as I am increasing the model complexity at the same number of examples, because more and more complicated models are there. So, I can certainly fit some model or the other better to the data. So, my training error keeps coming down, but my test error initially when model complexity is very small, because of very high bias, I get high test error. But if I make my model complexity very large, once again because of high variance now, I get high test error. So, somewhere in the middle, I have the best bias variance trade off, and that is what I need to get at. So, for example, if you think of this as a least squares fitting of a polynomial, and model complexity will be the degree of the polynomial. As we know, as we keep increasing the degree of the polynomial for a given number of examples, I can reduce my training error as small as I want, eventually make it 0. But if I have 100 data samples and I fit a 100-degree polynomial, obviously, even though my training error is 0, I am not going to say that this particular polynomial is what the data is generated from, right. So, the issue is that we need to select the model with the right complexity, right. Of course, we do not know which is the right complexity model, but certainly just going by training error does not help us. Okay. So, this we knew when we studied from our discussion on statistical learning theory. The error on training set is the empirical risk, and it is not necessarily close to the true risk, which is the expected error on newer test data, right. We saw that empirical risk will be close to true risk only when you have large number of examples. Large is relative to the model complexity, the VC dimension, right. So, otherwise, and in general at any given number of examples, if we increase the complexity, the examples will become small relative to the complexity. If the model class is very complex, then we will overfit. Overfitting means we are essentially getting low training error, but large test error. It is like we have fitting a 100-degree polynomial to 100 points, right. It is overfitting because we get 0 training error, but it is not certainly a very good fit, right. So, this kind of overfitting is what we want to avoid. We need to use the training data for selecting a suitable model class, that is model selection, estimating or learning a specific model from that class, and also to get the final learned model, right. As we briefly mentioned last time, if we have sufficient data, this can be done fairly easily. Okay. If data is no problem, then all this is not really problematic, right. What is the overall plan? If we have enough data, then whatever data we have, we split into 3 parts: a training set, a validation set, and a test set. The training set is what to use, like the training sets in all algorithms, that we repeatedly use the training set to learn a specific model from a chosen class of models. So, if I choose a neural networks with 1 hidden layer, 5 hidden nodes, then we use the training set and a backpropagation algorithm to learn the weights, right. Or if I chosen a SVM with a polynomial kernel with p is equal to 3, then for that model class we can of course use and a particular value of c, then we will then use the SMO algorithm, for example, with the training set to learn a specific SVM, right. So, for a specific model class, we use our training set to learn a specific model. What do you mean by repeatedly? What we are doing is, we are using validation set to select good models. So, let us say I want to know what is a good C to use in my SVM algorithm. So, I will fix some value of C, use the training set to get my SVM, then I measure the error of that SVM on the validation set. Now, I choose some other value of C, once again use the training set to learn an SVM, measure the error of this SVM also using the validation set. So, I use the validation set to compare different models. That is how you do model selection, right. And finally, after doing a particular model, after fixing my value of C and other parameters of the kernel in the SVM, I will learn my final SVM, and to get an idea of what its error rate is likely to be, I use the test set, right. So, essentially test set is not used till I come to the final classifier, as they say test set should be locked up in a vault. So, then because this is certainly new random data which are not seen in anything so far, right, they to give me a good estimate of the true risk. See, for example, if I use the validation set to assess the utility of the final learned model, it will not be good, because I chose that particular model class only because on the validation set that particular model class is giving me low error. So, I am likely to think that what I learned is very good, even though it may not be that good. So, that is the reason I need also a separate test set. So, basically if I have enough data, I repeatedly use the training set to learn specific models from a chosen model class. I compare different model classes for model selection using validation set, and finally, I use the test set to find the expected error of the final length model. So, validation set is used to find the error rate of the classifier and different model classes, maybe indexed by a parameter alpha. Alpha could be, for example, CFSVM. So, and then after choosing a particular model class and finally learning it, I use the test set to find its final error. Okay. A rough rule of thumb is you use about 50% data for training, 25% data for validation, 25% data for test. Okay. So, if you have 1000 samples, use 500 for training, 250 for validation, 250 for test. Okay. What part to use for validation, which 250 for validation, which 250 for test, which 500 for training. Well, normally, because you do not want any biases creeping in, we will do this in a random fashion. You split the data randomly into 3 parts with this in this proportion, and then use one for training, one for validation, one for test. Very often one goes through this several times, several random divisions like this and do this, just to see that the final classifier length does not change too much. Okay. If the final classifier length does not change too much, that means overall the learning is quite robust, and that will also give me sufficient confidence that whatever learnt is correct. So, instead of just doing one split of training, validation, test, one does many random splits of data like this, and on each of them you do the same process and compare the final length models to see if they are vastly different from one another. If they are, then maybe I am not learning well. If they are sufficiently robust, then it is fine. So, essentially, if we have sufficient data, this is what we can do. Right. What do you mean sufficient data? See, what we have just now advocated is that 50% of the data should be set aside for validation and testing, which means when I use my SVM algorithm or backpropagation algorithm or linear least squares algorithm, what have you, I am only using 50% of the data. That means, we are using only 50% of the training samples to actually learn a classifier. Now, this can restrict the complexity of the model we can learn. Right. So, if I have 1000 samples, I may be able to learn neural networks with 20 hidden nodes, but because I have to learn only from 500 samples, I can learn only with 10 hidden nodes, for example. Of course, things are not so linear, but in general, if the number of training samples is less, it restricts the complexity of model we can learn from. Now, this does not matter if I can get training samples at will, right. In synthetic problems, I can get as many training samples as I want, because training samples are simply simulated. Right. In some kinds of problems, for example, if I want web pages, right, possibly I can think I can get as many web pages as I want by crawling on the net, if web pages are my patterns. But in many applications, data is not easily obtained. Okay. So, obtaining data is a costly process, and then finding a classifier in the training data, every data should have its true classifier, true quote unquote classification label should be there, because you have to give data xi and yi. So, I have to obtain the data xi and then classify it. Both are costly. Obtaining data could be costly, also correctly classifying it could be costly. So, when data size is small, we are rather thrifty, and we do not want to permanently set aside data for other purposes. We may want to use all the data for training, right. Only then we can learn a model of sufficient complexity. So, when data size is small, doing what we advocated, having 50% for training, 25% for validation, 25% for test, may not be feasible. Okay. Let us just formalize all this so that we know what we are talking about. As earlier, let us say x1, y1, xn, yn is the training set. Let us say f hat is the model that we learnt, and L is the usual loss function. Then what is the training error? Training error, I will call it E train, is 1 by n summation I is equal to 1 to n L of f hat xi y. This is your empirical risk. This is the training error we have been considering in all our learning algorithms. Right. And when we want to do model selection, obviously there will be we have to also index different model classes. So, we will represent it as f hat alpha, where alpha is a parameter that denotes the model class. So, for example, number of hidden nodes or the value of C or whatever. So, when we are doing model selection and hence have to compare different model classes, this f hat may have a further subscript alpha. Now, the test error that we are interested in is the true risk. I call it E test, which is the actual expectation of the loss function, right. This is the true risk that we are interested in. When we have separate test data, we can easily estimate it as the sample mean from the test data, right. This is an expectation. If I separate test data, I will simply estimate it as L f hat xi yi summation over I 1 by the number of samples, where the summation is over all the test data, right. Now, whether it is test or validation, it is the same. In both cases, I want to estimate this, one for different alpha, one for the final f hat, but essentially we want to estimate this expectation as a sample mean on separate data. That is, what I am saying is, suppose we want to assess a model class, which is specified by parameter alpha. As I said, alpha could be value of C in SVM, number of hidden nodes and neural network and so on. So, if a particular alpha, we choose that model class, use our training data set to learn the right model, let us say that is f hat alpha. Then, to assess that model class on the validation set, I do L of f hat alpha xi yi summed over I. This summation is not over your training data, but over the validation data. So, if there are NV validation data points, there will be 1 by NV of the summation. Similarly, if I am doing test error, I do the same thing on the test. So, essentially the actual test error is a true expectation, which I can certainly use approximate as a sample mean if I have separate data, right. That is what we have been saying. Only if I do not have separate data, then taking the training error as test error is not right, because the f hat is specifically chosen to make the training error small. Okay. So, essentially I can do this, I can estimate the true risk as a sample mean like that, if I have sufficient data. Then we can do model assessment, model selection, everything like this. When the amount of data is small, my problem is keeping a part of it aside permanently for validation and testing. I do not want to do that. What can I do? So, we need some methods which can estimate the test error without having to permanently lock up data, part of the data. I want to use all data for learning, but at the same time, I somehow want to estimate these test errors more accurately. Okay. So, let us first start by looking at what is called an in-sample error. Okay. This gives you some theoretical ideas of what the problem is about. The in-sample error is the following. See, we have a training data xi yi, right. So, let us assume that for the same xi, we get one more measurement of yi. Normally, a lot of times is the yi noise, that is really the noise in the training data. So, let us say theoretically, let us for question of pattern recognition context, what it means is I take the same xi, go to some other expert and ask him to classify, right, or if I am actually measuring some value of some function experimentally, I set my data to xi again and remeasure yi and so on. Let us call that yi new. So, on the same xi, we get new yi new, and so this is a kind of in-sample training data. Xis are same, but yi's are once again obtained randomly using the same underlying distribution. And then we define what is called the in-sample error, which is L f hat xi yi new. This I take expectation with respect to the y new random variable, with respect to which this y news are obtained. See, xis are fixed, so there is nothing random in xi, right. That is why I am averaging over xi, but xis are fixed, but y new is random. So, I take an expectation over y new, and also have to take expectation over y, because the f hat that I have learned is a function of the old yi's, right. I have learnt f hat using xi yi. So, f hat is a function of the old yi's. So, this expectation averages out the f hat I could have learnt if I got some random data, and then having learned from there, this expectation tells me how I would have performed if the same xi, but different measurement noise was involved. Okay. Very often, if we think the the prediction variable is related to our measurement vector or feature vector x by a deterministic function f x plus noise, then a good way of assessing how well we learned is to just ask at the same axis, if I take a new measurement, how well my prediction predict the new measurement. This will tell me whether I am predicting the deterministic part or unnecessarily modeling the stochastic variation in the original yi using which I have learnt f hat. Okay. That is why we want to define the in sample error both as the expectation with respect to y new and expectation with respect to y. Okay. Now, we define what is a quantity called optimism as the in sample error minus the training error. Right. See, essentially the in sample error would be higher than the training error. Training error chooses an f hat, we choose an f hat to minimize the training error. The same f hat on new measurements will not do very well, right, will not do as well, I mean do okay, but will not do just as well. And because this is averaged over all first measurements, one expects in sample error to be higher than the training error. Now, essentially if it is small, then it is all right. So, we call this the optimism, in sample error minus the training error. So, if I can somehow estimate this OP, then I can get at least a connection between the training error and in sample error, in as much as in sample error is average over all possible measurement noise, right. If I can estimate that for my model, that itself gives me some good sense of how well my model will perform in general, right. So, estimating the optimism is a method of getting more accurate error estimates. If we think of fitting a linear model with d parameters and we assume that the relationship between y and x is f is equal to y is equal to f of x plus epsilon, where epsilon is a zero mean independent noise. This is the standard linear least squares statistical model. Then one can show that the in sample error is the expectation of the training error plus 2 into d by n times sigma square epsilon. D is the number of parameters in the model, n is the number of data, sigma square epsilon is the variance of the noise. Okay. Noise is zero mean. Okay. So, this can be shown for linear model learning. So, this gives us some interesting ways of doing model selection. Right. So, we can use estimates like this for doing model selection without needing separate validation data. There are many criteria, they call AKK information criterion, Bayes information criterion and so on, which essentially use such calculations to do a model selection without needing a validation data for model. Okay. These give good estimates in case of models that are essentially linear parameters. Most of this work for linear models. As we have seen already, linear models are essentially linear parameters. So, as we saw when we learned linear models, the most often used loss functions are the logistic loss function or the square error loss. So, all these estimates are for linear models and the square error loss are for logistic regression. Okay. So, we'll just look at one example of how one does that kind of model selection. So, let us say our model class is indexed by parameter alpha. So, I want to learn the right value of alpha to select a model class. We are in a model selection. So, what, as I said, alpha could be the number of hidden nodes, alpha could be C value. As a matter of fact, alpha could be not just as one parameter, it could be a vector parameter. So, alpha could consist of the C value as well as the parameters of the kernel function in an SVM, right. So, alpha could be a pair, an ordered pair, C comma let us say P is the degree of the polynomial kernel. So, different values of alpha specify different model classes and I want to know which model class to choose. Within each model class, I can find the training error because I have a training set. So, let us say E train alpha, E train as a function of alpha is the training error of the model I have learnt in the model class alpha, and let us say D of alpha denote the number of parameters to specify a model in the class alpha, okay, because we are considering only linear models. Essentially, as for linear class, alpha is not like C of an SVM. For linear class, alpha is simply equal to the number of parameters you use, the step size you use in the algorithm and things like that. So, let us say d alpha denote the number of parameters in the model class alpha. Then we define AIC alpha as E train alpha, this is the training error, plus 2 d alpha by n sigma square epsilon. So, essentially I am saying this is a good model complexity term. As you already know, the true error or true risk is empirical risk plus a model complexity term. In as much as my optimism estimate is given by this, right, we are saying in sample error is E train plus this. So, optimism estimate is this. So, this is a good estimate of the model complexity. So, we define AIC alpha as train alpha plus 2 times d alpha by n to sigma square. Of course, nobody gives you sigma square epsilon. Either you assume some noise variance model, or you make maybe a few multiple measurements and estimate as a noise variance. To make multiple measurements, I do not have to measure yi for each of the xi in as much as I assume noise is independent. At one xi, if I measure many yi many times and find the variance, that variance I can use here. Okay. So, the idea of this is that now I minimize AIC alpha rather than E train. Normally, when I am doing a learning algorithm, I am only minimizing training error. Now, instead of minimizing training error, I minimize this complicated thing, right. I want to, so it's like I am not choosing a particular model. So, I minimize this over alpha. Of course, in general alpha is a discrete parameter. So, one can't minimize this. So, but what it means is I choose different values of alpha, right, and then on each alpha I find the training error and then calculate this. So, the sum is the true reflection of that model class. Just because training error is small does not mean that the model class is good, because for example, d alpha may be large, right. That is what we have seen earlier, how the model complexity comes. So, these are some criteria for properly assessing the model complexity. So, I can use this compound thing for choosing a model. I can evaluate this for a few alpha and choose the best alpha. Whatever I gain compared to what I am doing earlier, I do not need a validation set now, right, because I do not need a separate validation error. I am using this estimate of optimism, right, to decide the model complexity term. So, I can use all the data I have for training. I do not need extra validation data. Okay. So, this is how, for example, I can do model selection. Okay. This is one this is called AKK information criteria. This is one way of doing model selection. Because in general, in sample error may not be the appropriate estimate, because that is the error that my land model will incur if I have the same xi, but do measurement for yi. Apart from that, we may not be able to get this kind of estimates in general, and that particular estimate we are given is for linear models under squared error logistic regression kind of loss function. So, in general, getting these estimates is also not easy for nonlinear models. So, what we actually need is some way to reliably estimate the test error, the true risk of a given model, using the same thing as the training data. Of course, I use the training data to learn f hat, but somehow I want to get the true risk of f hat somehow from the training data itself. That is what we want to do. Okay. Now, from our discussion on statistical learning theory, there are a few other possibilities one can think of doing this. For example, the test error is the true risk of f hat, and in the VC theory we have seen that the true risk of any model can be bounded above by an empirical risk and a term, and that term involves only VC dimension n and the training error. So, given the training error, I can certainly get a bound on the true risk of any model. Okay. So, if I have learnt f hat from some training data and I know the training error f hat, then knowing the VC dimension of that class, that model class, the number of examples and the training error, I can get a bound on e-test. We've seen such expressions when we did our, when we discussed statistical learning theory. In practice, these bounds may not be very useful for two reasons. As we saw when we derived these bounds, that these bounds are very loose. They are often use the so-called union bound, which essentially bounds the probability of union of sets by the sum of the sets. That itself is those bound. There are many other steps like that in the derivation, because of which the bounds are loose. The second problem with these bounds is we need to know the VC dimension of the model class. If you recall, we had almost more than half a class of derivation to get the VC dimension of linear classifiers in RN. So, in general, when we have a specific model class, finding the VC dimension may not be that easy. For example, for even neural network models, one has only an estimate on VC dimension, right, an upper bound on VC dimension. So, if you are using an upper bound on VC dimension and then an upper bound on the test, both of which are loose, ultimately the bound we get on the test error may be loose. So, by loose, what it means is that the true test error may be much smaller than the bound we get, but we unnecessarily think that our test error is very high. So, in practice, this may not be very useful. So, what we need are techniques, statistical empirical techniques that allow me to estimate the true risk or the test error using some of the training data. Okay. So, we'll start with one of the most popularly used such techniques, which is called cross validation. Cross validation is a very widely used statistical technique for estimating test error. Okay. In statistical parlance, the test error is also called generalization error, extra sample error to contrast it with in sample error. In sample error, we are using the same xi. The extra sample error is an estimate. So, essentially this expectation is like saying from the underlying distribution get new x and y, many new x and y, and on that sample estimate the error. So, that is why it is called extra sample error, generalization error, test error, all these are same, essentially the true risk of f hat. So, cross validation is a technique for estimating the test error without separately setting aside some data for testing or validation. What does cross validation do? Given the data, we choose some parameter k, we will come back later to say how to choose k is some integer and we divide the data of n points into k parts, roughly equal size. If you can get them to be exactly equal size, we will get exactly equal size, otherwise maybe one sample, one data point this way, that way. So, we divide the data into k parts. K is a parameter of the method, but to choose a k, we will discuss that later. But so, if I want to do 5 parts, so I may have 200 samples. So, I put 40 samples in each part. So, I make 5 parts, I divide the data into 5 parts. Then what do? Then I run the model learning algorithm k times. So, if I have divided my data into 5 parts, I am going to learn f hat 5 times. On the ith time, we use for training all parts but the ith one, and essentially use the ith part to estimate error of that length model. So, if I have divided my data into 5 parts, the idea is I run the same learning algorithm on the like this. First time, I set aside my first part, use parts 2, 3, 4, 5 for training. Then I will get some model. Then next time, I use parts 1, 3, 4, 5 for training, set aside 2 for testing. That is the second time. The third time, I use parts 1, 2, 4, 5 for training and set aside the third part for testing, and so on. So, we run the model learning algorithm k times. On the ith time, we use all parts but the ith part, that is 1, 2 up to I minus 1 and I plus 1 to k for training, and ultimately going to use the ith part for testing that model. And my final error estimate is a combination of all this. So, the idea is that I am not permanently setting aside any part of the data for testing or validation. Essentially using all data both for training as well as testing, right. It is an interesting finesse of dividing like this and doing sequentially. Okay. So, let us first set up some notation to actually write the cross validation estimate before talking about it. So, as earlier let us say x1, y1, x2, y2, x and yn be the data points. Now, we will talk about these various parts. So, let us say we are dividing the data into 1 to k parts, data is indexed by 1 to n. So, the division is represented by a function rho. So, rho is a function that maps the data indices 1 to n to part indices 1 to k. So, rho tells you which data sample is in which part, right. What does that mean? So, xi, yi, the data index is I. So, it will go into the part rho of I, right. That is how the rho is defined. Rho is an index function. So, if I want to know which part xi would be, which of the k parts xi would be, I just take rho of I and that part xi would be, okay. That is the definition of rho. Now, f hat of minus k be the model length when we leave out part k for testing and use all the other parts for training. So, f hat of minus 1 is when I use part 2, 3 up to k for training. F hat of minus 2 is the moduli length when I use parts 1, 3, 4, 5 so on for training and so on. So, f hat of minus k is the model length when we leave part k. So, which means what is f hat of minus rho I? Rho I is the index which specifies which part xi was in. So, f hat of minus rho I is the model length using a training data set which does not contain xi, right. So, if I say f hat of minus rho I of xi, it is the prediction of a model length, the prediction on xi for a model for which is length using training data that does not contain xi, right. F hat of minus rho I is a model length over a training data set that does not contain xi, right. I need this notation because my final error estimate is for each xi, I find its error on a model which is length without using it, right. Each xi is used exactly once for testing. So, I have to test each xi on a model that was length without using xi, and that can be represented under this notation as f hat of minus rho I xi, because rho I is the index of the part to which xi belongs and f hat of minus k is the model length when we did not use part k. F hat of minus rho I is the model length when I did not use xi for training. Okay. So, with this notation, the final cross validation error estimate, which we call ECV, is 1 by n, I is equal to 1 to n, L of f hat of minus rho I xi yi, right. Each xi is used exactly once for testing, but the prediction for xi is taken from that model which did not use xi for training. Right. So, this is the basic idea of cross validation. I use each data point once for testing and k minus 1 times for training, right. I do it k times. So, each data point is used both for testing and training, right. So, because I am not permanently locking up any part of the data and can get a fairly nice estimate for the error, because this is different from training error, because for on each xi I am using the model that is used, that is learned without using xi, and hence this is likely to give me a more accurate estimate of the error. Okay. So, the final error estimate is average of errors in predicting over xi when xi is not used for training. Right. Note that we are using each data sample once for testing and k minus 1 for training. That is the whole finesse of cross validation. We are not permanently setting aside any part of data for testing. However, to estimate the error, I am using of xi for testing with a model that was learned without having xi in its training sample. Okay. That is the reason for believing that this will be a good estimate. Okay. When we use k parts like this, it is called k-fold cross validation. Okay. So, the next see, we did not say whether this is validation error, test error, as you already seen, it does not matter. As a matter of fact, one of the most often used applications of cross validation is model selection. So, cross validation is used for model selection in the following way. So, for the model class specified by alpha, the validation error is called ECV alpha is given by this, where f at alpha is the model length from the model class alpha and f at alpha minus rho I is the model length with that particular part. So, this is how essentially I do cross validation. If I want to find the best value of C in my SVM algorithm, I make my data into 5 parts. For example, for many different values of C, for each value of C, I find the validation error of that value of C, that alpha, like this. With that value of C, I learn 5 different classifiers. First time using parts 2, 3, 4, 5 for training, second time using parts 1, 3, 4, 5 for training and so on. Then on each sample, I use the prediction of that model which did not use xi, and that is how I get the error, and that is the cross validation error for the parameter for that particular value of alpha. This I do for different alpha, and then choose the alpha that has the least value. So, essentially the alpha can be, as we said number of times, parameters of the model class, and we can essentially tune alpha using the above error estimate. So, for example, in most cases whenever you do empirical investigation of any pattern recognition algorithm, this is how you choose the parameters of the algorithm. This is how you choose the model class parameters. You use some k-fold cross validation for some value of k, 5-fold, 10-fold cross validation, okay, like this. So, essentially very often cross validation is actually used for doing model selection like this. It can also be used to estimate the final error after you learn the final classifier. After you choose a particular alpha, for that model class, you once again run it once, and that will give you the final cross validation error estimate for the final learned classifier. Okay. So, the whole idea of cross validation is I am not permanently setting aside any part of data for validation or testing. I am using all parts of the data for training as well as all parts of data for testing. Okay. That is a very interesting finesse. Now, what value to use for k? Now, this is not very easy to say. There is not a theoretically derivable issue. It depends on the amount of data we have, the complexity of the model, the kind of learning algorithm using and so on. Basically, the reason is the following. Given any class of models, the model has specific complexity. So, if I have too few examples relative to the complexity, I will not learn well. If I have sufficiently many examples, I learn well. So, essentially, for any given class of models, the expected error of the learned classifier decreases with increasing sample size. As we know, as the sample size increases relative to which dimension, empirical risk is a very good indicator of the true risk. So, we know that the expected error of the learned classifier decreases with increasing sample size. So, if we plot 1 minus test error, that will increase with the training set size, right, because error decreases 1. This is called the learning curve. So, if very few samples, I get very high error, but as the samples go to infinity, my error will be 0. So, this will go to 1, right. So, that is called a learning curve. Of course, for a given problem, for a given algorithm, we never have the learning curve with us, learning curve, but conceptually learning curve is an interesting thing to do. So, essentially, whether or not a given number of examples is adequate to learn from a particular model class, whether or not a given number of examples is learn this particular SVM with this kernel function, this particular neural network with this many hidden nodes, this particular linear model with this many parameters. Essentially, adequacy of a given number of training samples depends on this learning curve for that problem. We can hypothetical learning, most learning curves are like this. Of course, I put a kink here, not that learning curves have to have a kink, but they can have a kink. The idea is, when examples are small, each additional example improves your learning. After a while, slowly its effect tapers off, right. This is a general behavior of all learning problems. In the early stages, when you have very few examples relative to the complex model, every additional example is very useful in reducing the error. After a while, the effect of extra examples does not happen, because for this model class, this is already close enough to infinity, right. So, essentially the marginal value of extra samples depends on the slope of the learning curve at that point, right. In the initial part, the slope is very high, at the large part slope is very low, in between it varies, we do not know exactly how it varies, but there is roughly a knee like this. On all learning curves, there will be a knee like this. Okay. Now, the proper choice of k depends on how the learning curve behaves. Just to take one simple numerical example, suppose in a particular problem, this knee of the learning curve is around 120 to 140 samples, okay, somewhere around there. So, less than about 120 samples is not certainly adequate, but about 150 samples, 140 samples is always adequate. Right. With 140 samples, I have fairly good confidence of learning. At 120, my confidence is small, because that is the knee, and there can be a lot of difference between the confidence of at 120 and 140, because the knee is in between. Now, let us say we have 200 samples. Then if I do a 5-fold cross validation, if I do 5-fold, each part will contain 40 samples. I use 4 parts for training. So, every time my training set size will be 160. So, 160 is good enough to learn a good classifier. So, if I do a 5-fold cross validation, I certainly get, my training set sizes are fine, and also my test set size of 40 is also good, sufficient to give me a good estimate. But suppose instead of 200, I have only 150 samples. Then a 5-fold cross validation means each part will contain 30 samples. So, 4 parts will contain only 120 samples. So, it may not be a good enough training set size, right. On the other hand, if I do 10-fold cross validation, then each part will contain 15 samples. I use 9 parts for training. So, my training set size will be 135, which is close enough to 140. So, on the same problem, if I had only 150 samples, I may want to do 10-fold cross validation. Now, what is wrong in doing 10-fold cross validation earlier? Then also is okay, we have 180 samples for training. There is not necessary, because what is happening is, see, the whole idea of cross validation, because I am learning with different training sets, I learn sufficiently different F hats, so that the actual error I get is a true error. On different F hat minus k's are learnt here on samples where 40 samples differ from training set to training set. Here only 15 samples, if I did 10-fold cross validation, only 20 samples to differ from training set to training set. So, I may learn roughly the same classifier, so I may not get a good estimate. Okay? So, if I can give sufficient variability in the training examples learned by different classifiers, I am likely to get a better estimate, right. So, essentially, if I do too large, too many parts, I may get a high variance. On the other hand, if I do too small, I may not get enough, I may have a bad bias in my estimate. Right. So, basically, if I have 200 samples in this kind of problem, I can do 5-fold. If I have only 150, maybe I want to do 10-fold. Okay. A rule of thumb, most often one employs either a 5 or 10-fold cross validation, which is often good enough. An interesting special case of cross validation is what is called leave one out cross validation, where we choose k is equal to n, where n is the number of examples. So, I have as many parts as there are examples. That means, each example is its own part. What does that mean? Because I use k minus 1 parts for training and 1 part for testing, we train on all but one example and test on the remaining example. So, for each example, I leave one example out, train on the remaining examples, and whatever I learnt on that, I test on this example. Of course, my different training sets are very close to each other, right. So, but on the other hand, I am using exactly each example once for testing still on a model that is length without using it. Okay. Leave one out class validation, this is called leave one out class validation, because every time we are leaving one example. It's recommended when sample size is really low, right. As a matter of fact, though it may not sound like much, if you have sufficiently many examples, leave one out class validation in an expected sense gives you the true error. So, its bias is very low, but its variance can be large because you're doing leave one out, but its bias is small. So, the expectation of the leave one out class validation error estimate would be close to the true error estimate, true risk, if sample size is sufficiently large. Okay. But of course, this is also recommended sample size is low. Its main problem is it's also computationally very expensive. So, we do not want to go for it unless we really want to get this kind of an estimate, because you have to run your classifier learning algorithm n times here n is the number of examples you have. Okay. Essentially the error estimate is likely to have low bias, but may have high variance. Right? But this is one very special kind of a class validation estimate, which is called leave one out class validation estimate. Very often, even when data is large, if we can do it, one does this to get some estimate of the expected true risk. Also, is often resorted to when we have very small sample sizes. So, let us consider one interesting example of leave one out class validation. Let us say we are learning an optimal hyperplane using the SVM method. Okay. In SVM method, I do not have to do this learning multiple times to know what happens when I leave one example, right. That is why we chosen SVM for this example. We know that in the SVM, the hyperplane is completely specified by the support vectors. So, if we remove some of the non-support vectors from data, we would still learn exactly the same hyperplane. That is the nature of the automation problem. When we did the theory of SVM, we saw this, that the hyperplane is completely specified by the support vectors, and once having learnt it, now if we keep the support vectors and throw away some of the non-support vectors from the data and resolve the automation problem, we will get exactly the same solution. Which means, if I throw away some of the non-support vectors, then we will still learn the same hyperplane, which means the classification of all these left out data would be same as earlier. Right? We can use this to actually calculate what will be the leave one out class validation estimate. Suppose you have learnt a separating hyperplane. So, if we now remove any one of the non-support vectors from the training data set, we will learn exactly the same hyperplane, which means we correctly classify the removed data point. In leave one out, we are removing one x, learning f, and only on that x you are testing, and all those test errors are averaged. So, whenever I remove a non-support vector, I get 0. Let us say we are doing 0 1 loss function. So, I get no error, because I learn exactly the same hyperplane, and hence it will still classify the point as earlier. So, there is no error. On the other hand, if we remove any of the support vectors, I do not know. I may or may not learn the same hyperplane, and hence I may classify the leftover point wrongly. So, what is the maximum error I can get? When I leave out each of the support vectors, the length one may not classify the support vector correctly, the vector correctly. But whenever I leave out any of the non-support vectors, I will learn the same hyperplane. So, my error will be 0. So, which means my leave one out class validation estimate is bounded above by the fraction of support vectors. As a matter of fact, when we did support vectors, we stated that the expected probability of error is bounded above by the fraction of support vectors. This is essentially how it comes about, right. So, the leave one out class validation estimate is bounded above by the fraction of support vector. That is how fraction of support vectors is a very useful quantity in SVM, because it is a leave one out class validation estimate of the probability of error by the length classifier. Okay. Yeah, this is a feature that we already discussed earlier, but it is interesting to see its connection with the leave one out class validation estimate. Okay. And another method of doing the similar thing of using your training data to get test error estimate is bootstrap. Bootstrap estimates provide another general method of estimating test error, generalization error, true risk, whatever you call it. The idea in bootstrap is to generate many training sets from the given data by sampling with replacement. Sampling with replacement means I have x1 to xn, I choose a particular index randomly between 1 and n, put that data point into my this training set, then generate one more index set which could be the same as what we said. So, every time I generate a number between 1 and n, and that corresponding data I take into my training set. So, my training set may contain the same training point more than once, but by sampling with replacements like this, I can generate many training sets of the same size. So, the idea is, given the original data points, n points, we generate b number of training sets. So, first I generate n random numbers, each uniform distributed between 1 and n, that gives me one training data set. Once again I generate n random numbers, each uniformly distributed between 1 and n, that gives me one more training data set. Like this, given the original data of n points, we can generate any number of training sets. Let us say capital B is the number of training sets that we generate. The idea is then we learn a model on each of these B training sets, right, and the final error could be average of errors of all these models. Right. So, this is another method, it is called bootstrap, because it is essentially, of course, the same training data set, but using the same training data by repeatedly sampling, we are generating many training data sets and learning many different models and averaging out all their errors. So, the idea is just like the phrase pulling one up by one's bootstraps. Using the same training data, we are somehow getting at the test error. Okay, that is why it is called the bootstrap estimate. The main thing is, unlike in cross validation, we can have as many training sets as we want, all of size n, because we are sampling with replacement, we can keep generating as many as you want. B is at our control. See, in the cross validation, we cannot generate any more than n training data sets, right. I mean, because I can at most put n parts, right? I can't divide data into more than n parts, but here I can generate as many training data sets as possible. B can be anything. However, they can be very similar, that we will come to this later, we will later on see how similar they are. Okay. Once again, let us just complete the formalism. So, like earlier, let us say small b denotes the index of the bootstrap data set or bootstrap sample that we are generating. So, the capital B number of bootstrap samples. F hat small b denotes the model length using the bth bootstrap sample. Okay. Then the final bootstrap estimate of error is, I will first call it E1 boot, is, see this 1 by n, I is equal to 1 to n, L of f hat b x I comma y I is the training error, or is the error on the original data set, not, see b is not learnt fully on the original data set, it is learnt on some sample version of the original data set. So, this is the error or the estimate of true risk of the model learnt on the bth bootstrap data set, right, and I average it over all the b bootstrap data sets I have. So, the idea is that this is an interesting error estimate. Of course, there are two problems with this, at least one problem with this error estimate. Here we are using the original data set as test data, while for each b, f hat b is learned using some of the same data, right. So, essentially, if I want to call this second summation as the test error of f hat b, then it is like I am using x1 y1, x2 y2, xn yn as the test error, but some of these x's are used in training and hence learning f hat b. So, one does not expect this to become a very good estimate. So, this is not a good averaging. So, next class we will see a simple example of why this is not a good estimate, and then see how we can improve it. And then moving on from there, we are learning at many classifiers that can be learned from the same training data set. We will look at how we can make such a method become very effective by learning more than one classifier. Thank you.